We're going to pick back up with question 32 on our 5-11 Unit 5 test. Which of the following statements is false regarding electronegativity? I believe this is the first question we've had on electronegativity on the test, but what is electronegativity? Electronegativity is how well an atom can tug on electrons in a bond. So when there's electrons between two atoms, if you have a high electronegativity, you're good at pulling those electrons in the bond to you. If you have a low electronegativity, you're not good at pulling the electrons in a bond to you. Which of the statements false regarding electronegativity? Elements with high electronegativities also have high affinities. Well, if you have a high electronegativity, it means you are good at pulling electrons to you. Electron affinity is the energy change that occurs when you receive an electron. If you want the electron and it makes you more stable, you have a high affinity. So of course, if you need the electron, if you're good at pulling the electron to you, it means you need the electron. So that would be true. Why would you pull electrons to you, high electronegativity, if you didn't need the electron? Letter B. And if you don't need the electron, it means you would have a low affinity. Affinity is how much you want or like something. Elements in the lower left-hand corner have the lowest electronegativities. That is true. Why? Well, we know the size gets bigger top to bottom. Size gets smaller left to right. So the elements that are the largest are going to be to the left side because they get smaller left to the right, and they're going to be at the bottom because they get bigger top to bottom. So the biggest atoms are down here. The bigger you are, the further the electrons you are tugging are away from your nucleus, which is what does the tugging. The positive protons in the nucleus are pulling on electrons, but if the electrons they're pulling on in the bond are far, far away from it because it's large, it's going to be poor. It's going to have a low electronegativity. So that's why the ones over here are only 0.7, 0.7, and 0.7. 0.9. Why is barium a little bit bigger than cesium's electronegativity? It's because it's a little smaller than cesium. Size gets smaller left to right. So elements at the lower left would have the lowest electronegativities. In general, large atoms are the best at pulling. No, we just explained that they're the worst at pulling. Small atoms are much better at pulling because the small atom's nucleus is closer to the electrons they're pulling on. Letter C is false. Letter D, in general, high electronegativities have high ionization energies. High ionization energy means that you are pulling your own electrons tightly into you, making it difficult to pull off, requiring more energy, high ionization energy. But if you're good at pulling on your own electrons closely, you tend to be better at pulling other atoms' electrons to you more closely in a bond. True. In general, that's true. Now, the next question is taking a look at fluorine's affinity and chlorine's affinity. Fluorine's affinity is minus 328. Chlorine's is minus 349. What happens to electron affinity in general as we move top to bottom through a group or family? In general, the affinity should decrease top to bottom. But apparently it doesn't from fluorine and chlorine. What do we mean that the affinity in general increases top to bottom? Well, the bigger an atom is, the less it is able to accept an electron given to them, which is what affinity is measuring. If we look top to bottom, in general, it's going down. The affinities are going down top to bottom through many of these families. Chlorine down to bromine, down to iodine, down to acetone. Sulfur down to selenium, down to tellurium, down to polonium. Silicon down to germanium, down to tin, way down to lead. They're kind of going down. Aluminum down to gallium, down to indium, down to thallium. The affinities are going down. This is an affinity table right here. But fluorine's affinity is less than chlorine's. And we would expect it to be more because the trend's going down, but it's not. And this question's asking us to explain why not. Although both are high, why is fluorine lower? Is it because chlorine can satisfy the octet rule and fluorine can't? No. They both can satisfy the octet rule. They're both halogens. They both only need one more electron. They're 7A, or they're group Family Roman 7, group 17, they need one more electron to get 8 to fill that P. They both could satisfy the octet rule. Letter B, fluorine has a lower ionization energy. No, fluorine actually has a higher ionization energy. Fluorine's much smaller than chlorine. So it's harder to strip fluorine than it is chlorine. So that doesn't explain it. Chlorine has a larger radius. Yes, it does. But elements with larger radii have higher affinities. No, in general, they have lower affinities because the bigger you are, the less able you are to accept the electron. Your nucleus is too far away to really pull it in and accept it. So fluorine's smaller. It should be better at accepting it since it's so much smaller. But apparently it's not. Why? It's because fluorine, as it says here, is so much smaller that its electron cloud is very compact. In other words, fluorine's so small that it's hard to squeeze an electron in because that cloud is so small and compact that it will try to repel the electron you're giving to it. And that explains why the affinities here on this chart. Why is fluorine less than chlorine? Because it's too small. If it was just a little bit smaller, it would be higher, but it's too small. Oxygen's too much smaller than sulfur. That's why you can't even see oxygen on this chart. It's so much smaller than sulfur that it's hard to squeeze it in. Nitrogen has similar reasons. Boron has similar reasons. They're almost too small. The cloud's too small to squeeze an electron into it. Question 34. Which of the following statements is false regarding electronegativity? Is it the tendency to attract electrons in a bond? Yes, true. Is the scale first proposed by Pauling, does it have a range of 0 to 4? Yes. It's a relative scale, where 0 would be the lowest, 4 is the highest. But every element has a nucleus, so every element can attract electrons. So really, it only goes down to 0.7. But the scale could theoretically go from 0 to 4. 0 would be the absolute lowest. If you had no nucleus at all, you couldn't attract electrons to your atom. Is electronegativity positive, negative, or 0? No. It's a relative scale. It's comparing. There is no negative electronegativity. You can't have a negative pull. A negative pull would be a push. So electronegativity is only 0 to 0.4, really 0.7 to 0.4. Only electron affinity can be positive, negative, or 0 since it's measuring a change in energy. It's a relative scale. Electronegativity is a relative scale. So it can't be negative. Letter D, elements with high electronegativities have high affinities and high ionization energies and small radius. In general, that's true. If you have a high electronegativity, you need electrons, which means you have a high affinity for them. If you're good at pulling other electrons, high electronegativity, it means you're good at pulling your own electrons, high ionization energy. Ionization energy is how tightly you pull your electrons. Small atoms are better at pulling, so they would have high electronegativities. Does the electronegativity have known units? True. Electronegativity number doesn't have units because it is a comparison between atoms. It's a relative scale. An actual scale would be if you were measuring their pull. You're just comparing their pulls. Question 35. Ionization energy tends to increase left to right. Yes, it does, but there are exceptions. What best explains why boron has an ionization of 800 and beryllium has a higher ionization of 900? Because in general, left to right, they go down. 520, or they go up. 520 goes up to 900. Then it drops a little bit. Then it goes up to 1090. Then it goes up to 1400. Then it drops a little bit. Then it goes up to 1680 and then 2000. So in general, it increases ionization energy left to right because the atoms are getting smaller. But here, boron is smaller than beryllium, but it has a lower ionization energy. Why? We've kind of dealt with this before. They're looking for the reason that best explains it. Look at letter C. Boron is S2, or beryllium is S2 configuration. Beryllium is an S2 configuration. Boron is S2P1. Second column has 2 in the S. 2 in the S is somewhat stable. So it's harder to pull that electron out of the S because the S2 affords beryllium some stability. Whereas with boron, it's easier to pull it out because boron is S2P1. That electron in the 2p1 has higher energy. So it's out there further from the nucleus, meaning it's not going to be held as tightly. The 2p1 has higher energy. That electron's further from the nucleus. It's easier to strip. How much energy does the 2p electron have? It has an energy of 3. Why? When you're in the p, your second number is a 1. Your first number is 2. 2 plus 1 is 3. When you're in the 2s, the total energy is 2, because when you're in the s sublevel, your second number is a 0. 2 plus 0 is 2. Back to that off-bio order of filling stuff. So that explains why the 2p1 electron is easier to remove than one from the 2s in beryllium's case. These other reasons are definitely false. Do the radii increase left to right? No, they decrease. Letter B, boron has a lower ionization energy because boron is smaller than beryllium and it takes less energy. Well, the radii do decrease left to right. Boron is smaller than beryllium, but it takes more energy in general to strip one from smaller. So we would expect boron, since it's smaller, to take more energy to strip. It doesn't. Letter C explains why it doesn't. It's because of their configurations. Ionization energy depends a little bit on the configurations. In fact, question 21, what factors affect ionization energy? Radius does. The smaller you are, the harder you are to strip. Nuclear charge, the more protons you have, the harder you are to strip. That's because the more protons you have, the radius gets smaller. Shielding effect, the more shielding effect you have, the easier you are to strip because the electron you're stripping is shielded from the pole of the nucleus. And then electron configurations, which is what letter C is talking about. Boron has a lower, letter D, boron has a lower electron affinity than beryllium because boron has a higher ionization energy than beryllium. Well, actually, boron has a higher affinity than beryllium, not a lower affinity. So it's wrong right there. And actually, the greater affinity you have in general, the greater ionization energy you would have as well. So those atoms that want another electron badly, it makes it harder, or in general, it is harder to strip the electrons they already have. We'll pick back up with question 36 in hopefully one of our final videos.